Okay, so we're going to talk about cloud formation today, and we saw we made a cloud in class yesterday, and you saw it in the bottle, and you will be making a cloud in a jar in lab. And so we're going to talk about what happens in the real world, out in weather for making clouds. And one of the big things, as we saw in the lab and in class, is condensation. Condensation is just, whoops, sorry about that. Condensation is just the change of phase from a water vapor into liquid water. We've seen this. Think about some examples. We saw it in the lab in the relative humidity and dew point lab. Some examples of that, as you saw in the lab, that cold, when you have that cold can of water, water will condense out of the air going from a vapor. That water didn't just seep through the can, it was condensing on the outside of that can from the air. If you take a hot shower, it's a cold day, the mirror's cold, the steam, the hot, humid air from your shower is filling that room, and as it hits that mirror, the air cools down, and as it cools down, it reaches its dew point, and you get dew on the glass, dew on the grass, and then fog or clouds. Clouds and fog are really the same thing. Fog is just clouds at ground level. So they're really one and the same. As the air temperature drops in the evening and during the springtime right now, you might wake up in the morning and it might be really foggy. And it's foggy because it was humid, like today. It's raining right now. And tomorrow morning, when you get up and you come to school, you might be driving through fog because the temperature is still dropping at night and it gets down to the dew point, and bam, you get fog, which is basically just a cloud right at ground level. So think about this. What do you need for condensation to happen? What are those things? And we saw it in the cloud in the bottle. What were the things that we needed to do? We needed to have water vapor, obviously. We need to have something for that water vapor to condense on, condensation nuclei. And we also need, to get the air to saturation. Need to get that relative humidity to 100%. If you remember from our relative humidity notes, as you cool the air down, relative humidity goes up. So cold air can't hold as much water vapor, and so as I shouldn't say that it can't you can't get as much evaporation in cold air, and so what happens is the air can't have as much water vapor in it, and so as you cool that air down, it reaches its dew point, and bam, you get 100%. Cool it down just a tiny bit more, and that water has to come out. There's no place for it to go. You get more condensation than you get evaporation, and so you get condensation on the dust and dirt in the air. And when that happens, we get oops, sorry about that. Uh, we get the temperature changes. And this is one of those things that we saw with the sling psychrometer. Water's evaporating, so you have to add heat to it, and that added heat causes the thermometer to go down. When you have it go the other way, when water condenses, it releases heat, and this is will become important when we start talking about cloud formation in a second here. Um, One of the ways that we can get this air to get to the relative humidity of 100% is by getting the air to move. And this is where we finally get into start talking about some weather. And what I want you to see here is this. So as we can connect this air pressure and dew point now into a way that makes sense for what we see in the real world. You get air down here at the surface. It may be warm. And as it goes up, what happens to the pressure? The pressure goes down because there's less air above you than when you were down here, and so there's less pressure pushing down on you. So the air cools. Well, it cools because when there's lower pressure, as we saw with the bottle and the fizz maker, as I released that pressure in that plastic bottle, the air pressure went down and the temperature went down. And there's something called the adiabatic rate. And adiabatic cooling is just cooling because the air expands. And when air pressure decreases, air expands and it cools the air down, and it cools it down at a pretty consistent rate, about 10 degrees per 1,000 meters until it reaches the dew point. So as this air rises, the dew point, or sorry, the air is expanding because there's less pressure. It's cooling down until you hit the dew point. And once that dew point's reached, the air starts to condense. The water starts to condense on particles in the air, and you get a cloud to form. Now, when that air continues to rise, it is continuing to cool down, but it doesn't cool down as fast because condensation is happening. And check this out. This is a really cool concept. As you get condensation, you actually release heat into the atmosphere. So the air doesn't cool down as fast because you have condensation happening. So when you're up here and the air is continuing to rise, it doesn't cool as fast because when it condenses, it releases heat back into the atmosphere, and it still cools, but not as fast. Down here, there's not that release of heat energy because we don't have that change of phase. And so as this air rises, it cools down, but it cools down much more quickly. So how is it that we can get air to get pushed up? Because that's one of the ways that we can get condensation to happen is to make this air rise. And as that air rises, it'll cool. So we want to get that air cold. One of the ways to do that is because when you have warmer air, it starts to get less dense. And as we know, warm air expands, it starts to rise, and once it rises, once that rising occurs, then you start to get that less pressure, and then it starts to cause it to cool. Now, it doesn't mean that once that that warm air starts to rise, it gets cold, and then just because it's cold, it starts to sink. What happens is this air is warm, right? If you compare it to the air temperature around it, it's still warmer than the air around it. And so it continues to rise. So even though the air is cooling down as it rises, it may be 12 degrees, but the air around it might be at 10 degrees. So it's still less dense than the air around it, so it continues to rise. And this air at 2 degrees may be still just a little bit warmer than the air that's around it at 0 degrees or -1 degree. And so it continues to rise. So once you get this air started at 32 degrees, once it starts rising because the air around it is cooler, it will continue to rise, even though it's cooling off. I know it seems counterintuitive that that would happen, but because this air warms up from the sun, it starts to rise and it begins to cool down, and then we eventually will hit the dew point and you'll get clouds to form. Now, these clouds, as we were talking about before, and I've talked on and on about that, but this is what we get. Warm air rises, it maybe have some water vapor in it, it expands and cools because of that release of pressure. It's that adiabatic cooling. Air becomes saturated, it hits the dew point, gets 100% humidity, water droplets form on the dust particles, and then boom, you get a cloud. And clouds are not water vapor. They're drops of water, or in most cases, actually, they're ice crystals. So because it's below zero, when you finally reach that dew point, as the air gets pushed up, you get these ice crystals form. And they remain aloft until those water droplets get big enough that the air can't support them. And there's a few ways that the air gets pushed up. As I talked about this adiabatic cooling, it's this cooling because it's rising. The air is rising through the atmosphere. And, sorry, I'll try and put that over here so that you can see it. Air is rising through the atmosphere, and as it rises, it cools because it's got less pressure around it. There are four ways that happens, four ways that air gets pushed up. One is convection, and we've seen convection before. We've seen it in the Earth's center, of the Earth, where the center of the Earth is warmer than the outer parts. That heat is coming out from the center and it's moving towards the surface, and that molten rock rises from the center and it spreads out at the surface and then sinks back down. So that density differences as the air warms close to the ground because the sun's hitting it, it starts to rise because it's less dense. exact same thing that's happening in the center of the Earth. Instead of air, it's sort of molten rock or the heat in that asthenosphere that is moving that semi-molten plastic mantle. Just like the lava lamp. Same thing. When we talk about air, we talk about it as being a fluid. Um, Air acts like a fluid, water acts like a fluid, liquids are fluids. They behave in physics very similar. They're very similar in that way. And so we can talk about them in similar terms. Something called orographic lifting, and this orographic, this prefix is something we've seen before. If you remember back to the Earth's history, on page 9 in the reference table, we've got those orogenies, which were the mountain building events. Or orographic means mountain, um, the being running into mountains. So the air, as the air hits these mountains, it causes that air to rise up. Uh, Mountains block that airflow and cause it to be pushed up. And so we see, I'll give you a second to write that down. We see this orographic lifting airflow. This is a perfect example is the west coast of the United States, the Rocky Mountains, the Sierra Nevada mountains, the Cascade Mountains in Washington. All of those mountains are near the Pacific Ocean. We get warm, humid air coming in from the ocean, and it has no place else to go. It has to go up. So it gets pushed up, and as it does that, the air cools down because of that adiabatic cooling, hits the dew point, and you get clouds and rain. As it goes back down the other side, just the opposite happens. You get adiabatic heating, and it warms up the air because just like in the example of the bottle with creating pressure in the bottle, it creates increases the pressure, and you get more heat in that air, and it dries the air out, so the relative humidity goes down. Here's that localized convection. Heat rises, warm air rises, the warm air expands and rises until it gets to the dew point. A couple other ways, something called frontal wedging. We'll talk about this more when we get into air fronts, and convergence, where two air fronts, two air masses come together from opposite directions. There's no place else for them to go but up. Some air gets forced out to the sides, of course, too, but mostly it's freer to go up in the air. Frontal wedging is when warmer air rides up over colder, more dense air, and you can see it here. A warm front will be moving here and rising up over this cold air. And convergence, you can see here's the United States, and air may be coming in from the east and from the west, or from the southeast more likely. And when they converge, the air gets forced up. No place else for it to go. And as it gets pushed up, you get clouds. So anytime air gets pushed up, you get clouds. Anytime the air rises, you're going to get clouds if there's enough moisture in it and if it reaches the dew point. And then eventually, once the cloud particles get too heavy, the water droplets in the air get too heavy, they're too heavy to be suspended. They fall to the earth. We get precipitation like it's happening right now, and it can be depending on the temperature. Whatever the temperature is, that determines what kind of precipitation you get, whether it's rain or snow or any of those sorts of things. So this is cloud formation, super important in terms of weather. This is really important. You got to know what causes these clouds to form and the effects, what causes the air to be pushed up and have this adiabatic cooling. These four are really key as well. So this is super important, and these we'll talk more about in class. Thanks so much. Talk to you later. Bye.